In the spring of 1816, people across Europe and North America noticed something deeply wrong with the sky. As daylight arrived dim and colorless, and the sun appeared weak as if filtered through permanent haze. Temperatures dropped without warning, frost returned in months that should have been warm, and crops failed in fields that had produced food reliably for generations, leaving communities confused and unprepared. No one connected these changes to a volcano on the other side of the planet, because Mount Tambora had erupted more than a year earlier, thousands of kilometers away, on an island few outside the region had ever heard of. The eruption itself was brief, violent, and catastrophic, but what followed was far more unsettling, as the atmosphere began to change in ways people could not see, measure, or understand at the time. The skies did not darken because the world was ending, but because Earth's climate system was responding to an extreme disturbance, following physical rules that do not stop applying simply because humans are caught beneath them. Mount Tambora erupted in April 1815 on the island of Sumbawa, releasing an explosion so powerful that it was heard more than 2,000 kilometers away, long before anyone understood what had actually occurred. The eruption ejected an enormous column of ash and gas high into the atmosphere, far above weather systems, injecting material directly into the stratosphere, where it could remain suspended for years. This was not a typical volcanic eruption, but one of the largest ever recorded, classified today as a Volcanic Explosivity Index 7 event, placing it among the most extreme natural disturbances in human history. In a matter of days, Tambora expelled tens of cubic kilometers of material, stripping the mountain of much of its height and devastating nearby regions through pyroclastic flows, ashfall, and atmospheric shockwaves. But the true global impact of Tambora did not come from lava or ash on the ground. It came from sulfur-rich gases that spread silently through the upper atmosphere, setting the stage for a climate disruption no one was prepared to face. When Mount Tambora erupted, it released vast amounts of sulfur dioxide into the upper atmosphere, a gas that does not simply disappear, but reacts with water vapor to form tiny sulfate particles suspended high above the Earth. These sulfate aerosols spread throughout the stratosphere, carried by global wind patterns, forming a thin but persistent veil that reflected incoming sunlight back into space before it could warm the surface. Unlike ash, which falls out of the sky relatively quickly, these particles remained aloft for months and years, continuously reducing solar radiation and lowering global temperatures in a slow, cumulative process. The result was not darkness in the sense of night, but a muted world where sunlight appeared weaker, skies took on strange colors, and seasonal temperature patterns began to shift beyond anything recorded in living memory. This atmospheric response followed physical laws, not chance, showing how a single extreme eruption could disrupt the balance between sunlight and climate on a planetary scale. Because the sulfate aerosols formed in the stratosphere, above most weather systems, they were not easily removed by rain or wind, allowing their cooling effect to persist far longer than the eruption itself. As sunlight was repeatedly reflected away, surface temperatures dropped gradually rather than abruptly, creating a delayed response in climate systems that people could not immediately connect to the eruption. This cooling disrupted atmospheric circulation, shifting wind patterns and altering the timing of seasons, which caused cold air to linger longer in regions that normally warmed by spring. The climate did not collapse all at once, but drifted into instability, as small temperature changes compounded over time and pushed agricultural systems beyond the margins they depended on. By the time the effects became undeniable, the aerosols had already spread globally, locking the planet into a period of abnormal climate that could not be reversed quickly or locally. As the aerosol layer thickened, its effects varied by region, with some areas experiencing sharper cooling while others saw increased cloud cover and prolonged periods of unusual weather. This uneven response occurred because the atmosphere distributes energy through complex circulation patterns, meaning the same volcanic disturbance can produce different outcomes depending on latitude and season. In the northern hemisphere, where much of the world's agriculture was concentrated, these shifts arrived at a critical moment, interfering with planting, growth, and harvest cycles. The climate system did not fail catastrophically, but it lost reliability as temperature and precipitation patterns no longer followed the rhythms farmers and societies depended on. This loss of predictability, more than extreme cold alone, set the stage for widespread disruption, transforming a distant eruption into a global human crisis. As cooling persisted, ocean temperatures also responded, reinforcing atmospheric changes and extending abnormal weather patterns beyond a single season. This interaction between oceans and atmosphere amplified the original disturbance, allowing a brief volcanic event to influence climate behavior over multiple years. Volcanic aerosols gradually dispersed and settled out, but the systems they disrupted required far longer to return to balance, revealing how sensitive climate equilibrium can be to short-lived shocks. These processes demonstrate that extreme eruptions do not need to be continuous to be devastating, because their strongest effects unfold after the eruption has already ended. By the time the atmosphere began to clear, societies were already dealing with consequences that no single nation or region could isolate or avoid. For people living in 1816, none of these atmospheric processes were visible, measurable, or understandable, leaving communities to experience the effects without knowing the cause. Weather no longer behaved as expected. Seasons arrived out of order, and familiar patterns that guided farming and trade began to fail without explanation. What made the disruption especially dangerous was not its intensity, but its persistence, as abnormal conditions continued month after month with no clear end. As harvests failed and food supplies tightened, the consequences moved beyond climate and into society, affecting economies, migration, and public health. By the time the link between Tambora and global climate was eventually understood, the damage had already reshaped lives across continents, turning a distant eruption into a shared human experience. In Southeast Asia, the eruption's impact was immediate and devastating, as thick ashfall buried villages near Tambora, destroyed crops, contaminated water sources, and collapsed local food systems within weeks. Beyond the immediate blast zone, cooler temperatures and disrupted rainfall patterns affected regions across Indonesia, India, and parts of China, where monsoon timing became unreliable and harvests failed. In many areas, famine followed climate disruption, not because temperatures alone were extreme, but because agricultural calendars no longer matched the environment they depended on. Historical records describe shortages, disease outbreaks, and mass displacement as communities struggled to adapt to conditions that persisted far longer than any single season. For millions across Asia, Tambora was not remembered as a volcanic eruption, but as years of hunger and instability caused by a climate system pushed out of balance. In Europe, the year 1816 became known as the year without a summer, as cold rains, late frosts, and persistent cloud cover destroyed crops across Britain, France, Switzerland, and Germany. Grain harvests failed repeatedly, food prices rose sharply, and shortages triggered unrest in many regions, exposing how tightly European societies depended on stable seasonal weather. Across the Atlantic, North America experienced similar disruptions, with snow reported in June, frozen rivers during summer months, and widespread crop failures throughout New England and eastern Canada. Families abandoned farms, migrated westward, or relied on emergency aid, as communities struggled to survive conditions that no previous generation had prepared for. What linked these distant regions was not politics or trade, but a shared vulnerability to atmospheric change, revealing how a single eruption could reshape human history far beyond its source. Across different continents, the same sequence repeated, as a brief volcanic eruption triggered atmospheric changes that unfolded slowly, unevenly, and far beyond the place where they began. The disruption did not move outward like a wave, but settled into global systems, altering sunlight, temperature, and rainfall in ways that no single region could escape or counteract. What made Tambora unique was not only its size, but its ability to interfere with the delicate balance that connects volcanoes, atmosphere, oceans, and human survival. These patterns reveal that extreme natural disasters are rarely isolated events, but system-level responses that emerge when physical limits are exceeded. Tambora showed that the most powerful forces shaping human history are often invisible at first, unfolding gradually as the planet adjusts itself according to rules that do not bend to human expectations. The eruption of Mount Tambora did not destroy the world in a single moment, but it altered the conditions that sustained it, showing how deeply human societies depend on stable environmental systems. What made the disaster so devastating was not the explosion itself, but the delayed consequences that unfolded quietly through climate, agriculture, and human survival. Tambora reminds us that extreme natural disasters often operate on timelines far longer than human attention, reshaping lives through persistence rather than spectacle. The skies eventually cleared, temperatures recovered, and ecosystems adjusted, but the social and economic scars left behind lasted far longer than the eruption that caused them. This pattern has repeated throughout history. As Earth's systems respond to extreme disturbances according to physical laws, not human schedules or expectations. Understanding these processes does not make such disasters less severe, but it allows us to see them not as random acts of destruction, but as predictable system responses when limits are exceeded. When the sky turned dark after Tambora, it was not a sign of the world ending, but a reminder that the planet we depend on is governed by forces far larger, slower, and more persistent than we often realize.